Good evening, everyone. My name is Benam Shaderek, and I'll be taking you through the exploratory data analysis for our data set, which is TPAVA data set, which is the data set we're going to use to train our machine learning model for, which is basically to detect for early prediction of viscous fever. So the first thing we're going to do is to upload the data set, which we have done using this line of code. We are going to upload it to Google Colab. Then after, I've already done it here as we see. Then after, this line of code is going to enable us to load this data set which we have uploaded to this interface which we are using. Then next, we're going to import libraries. So the libraries which we are importing. The first one is pandas, which is for data manipulation. Then we import simple imputer, which is to handle missing data. Then label encoder for converting categorical data into numerical form. And then standard scaler normalize the numerical features. Then next we are going to load the data set using this line of code, pd.read csv. Then we write the name of the data set, and you must make sure the name is correct because otherwise it won't work. And then we specify the delimiter to this t. Then this is going to read the data into a data frame. The delimiter is going to read the data into the data frame, which is like an Excel table in Python. Next, we are going to identify missing values, and this is done using this line of code. df.isNull.sum, and then this is going to count the number of missing entries per column, and then we filter out to show only the columns that have missing values, and this is going to help us to focus on problem areas without getting overwhelmed by unnecessary data. So, and if I can show you, first of all, our data set has various columns. It has the name, genotype, ECF, farm cell, longitude, latitude, XEPSG, YEPSG, tick, cape, buffalo, bio. And once we have identified the missing values, it is returning that the genotype has 20 missing values. The tick, cape, cattle, bio 5 all have three missing values. That means the rest of the columns have full data, they don't have any missing values. And as we have said, this is going to help us to focus on the problem areas without getting overwhelmed by unnecessary data. Then next we are going to imputing missing numerical values. And another thing I want us to realize is that we have a number of missing values in our data set. Well, we have NA. So for numerical columns, we are going to first select the D types. For numerical columns, we are going to first select them using D type. Select D types. Then after, we are going to create a simple imputer with a strategy set to mean, meaning the missing values will be replaced by the average of that column. So that means all these missing values will be replaced with the mean of that column, and that's how they are going to be replaced, so that we don't have any missing values. So we are trying to handle the missing values. Then after, it's going to use the feed the transform function, and this is used to overwrite the original columns with the cleaned data. Then next, you're going to imputing missing categorical values, and the process is similar, but here the main difference is that we are going to set the strategy to most frequent. Taking it back to our original data set, as we see, this column for the genotype, they are categorized into only two. There is 54K and then there is 800K. So since we have set the strategy to since you have set the strategy to most frequent, that means it is going to replace all these NAs with the most frequent category in this column. And the process is still similar. We are going to select the numerical select the numerical columns using select D type C. Then we create a simple imputer by setting the strategy to most frequent. Then we set the fit transform, override the original columns with the clean data. Then next we are going to encode in categorical variables. And now one thing we have to know that machine learning models can't handle text directly. So we have to convert the categorical data into numbers using the label encoder. And for each categorical column, we have to first initialize the encoder. We have to, which is here. Then we apply the fit transform, which is this line of code, to convert the categorical features, to convert the categories into numerical labels. And then we are going to store the encoder into a dictionary for future use. And one thing you have to know that the storing these encoders is crucial, because once we get new data later, we can apply the same encoding without any inconsistency. Now, if I'm to illustrate, we see, I don't know if I have any data which is in form of categories, but I think we have understood that machine learning models can't handle text directly, so we have to convert that text into categorical data using the function of label encoders, and I've just explained how it works. So next we are going to normalizing the numerical features, and we do that using the standard scaler. And this standard scaler standardizes the data by subtracting the mean and scaling it to unit variance. And we have to understand why is this important. This is because the machine learning algorithms like KNN, k-nearest neighbor, or logistic regression, they perform better when features are on a similar scale. And specifically, this is the line of code that does this. We normalize the numerical features using the standard scaler, and as I had said above, the fit transform to overwrite the data, it will override the original columns with the cleaned data. Then lastly, we are going to save the preprocessed data. After all the transformations you have done, we are going to save it using, we are going to save it as pre-processed dataset.csv, and another thing you have to note here, which is very crucial, that we have to set the index to false, and this is because we have to prevent the data frame index from being added as an extra column. Once we add true, once you set it to true, the data frame index will be added as an extra column, which we don't want in our new data. So we set the index to false, so that we don't add the data frame as an extra column, because it will stand out to be confusing for the machine learning algorithm which we're trying to teach. Then lastly, we print. This message has to come, because once it doesn't come, like it's like a confirmatory message. Once it doesn't come, that means the data has not been saved. Once it comes, that means the process has been successful. So that's it. Thank you very much.
Good evening. I'm Katenja Brendan. I'm going to continue from where my colleague stopped. He talked about pre-processing of data, where he talked about replacing missing values, and also encoding the values that have alphabetic figures and to make them numerical, enable machine learning. So we are going to continue and do exploratory data analysis. First of all, we are going to import some libraries. We are starting with pandas, of course, which is used for handling datasets. And also, we are going to import Seaborn This one provides the statistical data visualizations, as we shall be having histograms and some graphs. We shall also import matplot.lib. This one is also used for plotting graphs. We shall import numpy. Numpy is for supporting numerical operations, and also we shall import imblan for undersampling, for making classes even, or for making them to be equal, so that they do not create some bias during training of the model. So we are going to start with loading the dataset. Remember, after this pre-processing, our dataset was now saved as pre-processed dataset. So we shall first load it, and then we shall convert the binary values into integers. For example, if the ECF value is greater than 0.5, it is signaled as 1. If it is less than 0.5, it is signaled as 0, indicating the presence of East Coast fever and then indicating the absence respectively. So we shall also continue and perform undersampling. Undersampling reduces the majority class size to match with the minority class size. We shall be seeing this in the graph later before in visualizations. Make the ECF which are positive to be equal with the ECF which are negative, 0 and 1 respectively. This undersampling, X contains all feature columns, Y stores only the ECF columns for target variable. It balances the dataset by randomly removing samples from the majority class, and also the new feature is set X for resampled, and then the label Y is resampled, which contains an equal number of cases for both ESF 0 and ESF 1, which means negative and positive respectively. So after doing this undersampling, we shall go ahead and save this dataset using this line of code. DF resampled CCF. It has been now converted from the pre-processed dataset into this analyzed dataset.csf. Index is equal to false, and then we shall print out this dataset as I will be showing you here in visualizations. So we shall go ahead and then do the actual data analysis since we have finished balancing this dataset. So the first one is that we are going to do class distribution. It is here is SNS with count plot. X is equal to CSF. Data is equal to D that we resembled. Then we shall have this balanced ECF class distribution. It is here in the visualizations. Let me see. Yeah, it is right here. And see the balanced ECF class distribution. Here down it shows the 0, which is absence, and also here it shows the 1, which is the presence, and we can tell that both of them are approximately at 150 when we are talking about the count. So this one shows that our data has actually been balanced. This is the output I was talking about after the sampling has been done. This is the sampled analysis of the data set. We can see the mean, we can see the counts, and also we can see that the ESF here has also been balanced. We have equal ones and equal zeros, which indicates the presence and absence of the ECF. So we shall go back to our code and then perform another exploratory data analysis, which will be for correlation of heat map. Remember, we loaded this library, so we shall have an output of a heat map which has some matrix correlations for the features we are going to use. For example, here we can see name and also the name. You can see that they have a strong correlation between them because they are in red, and also we can see the genotype and the name, they have some weak correlation. When we are to look about this, you can see that this blue actually some weaker correlation, and also the farm and the name, they have weaker correlation in terms of determining the ESF presence in a particular cow or in cattle. So let us take a look at the strong. Take a look at the strong correlations. We can see the genotype here. It has a strong correlation, the genotype of course. And also let me take a look at this longitude and the cell. We have the longitude. You can see they also have a strong correlation with the latitudes. And also let me take a look at the genotype and the tick. The tick is here. Look at the genotype. We can also see they have some weak correlation, though it's not totally weak. So this is the heat map that has the matrix correlation of the features, how they depend on each other, and how they affect the prediction of the ESF in cattle. So we are going to perform another EDA, which is of histograms. We shall going to use this code of df desampled.histogram. Then we shall have determined the size of the histogram, which is 12 and 10. So we shall have an output. Output is right here. It has various histograms of different features. We have the name, we have the genotype, we have the farm, we have the cell, we have the longitude, we have the latitude, we have the cape buffer, of course, which spreads this stick. We have the cattle, and then we have the bio, which records the temperatures. So talking about the histogram, shows the distribution of for each feature, shows the mean, the medium, the interquartile range, and the box. So take about the key insights about this. Have the name feature has the highest range and many outliers. As you can see here, the outliers are very many compared to the genotype. And also the farm and cell show some moderate ranges, while these others talk about the longitude and latitude. They have a lot of outliers. The tick, the Cape Buffalo, and ESF have fewer outliers. So since that we are spending more on the tick and the Cape Buffalo and ESF, which have relatively few outliers, and guarantee ourselves that this data will be accurate, since this longitude and latitude will be an alternative during our testing. We shall go back and use and perform another EDA of box plots. This EDA helps in identifying outliers, and also it drops ESF since it is categorical. We shall perform another EDA, which is of box plots. It shows the tick infestation levels, the x-axis, and also the ESF presence in the y-axis. So let us take a look about this visualization of the box plots. It is right here. It is here. It helps you to visualize if the tick infestation has a clear relationship with the ESF. So we can see that the ESF is on the y-axis, so it is higher, while this tick infestation is on the y-axis, on the x-axis. So we can see that the cell, the farm, the genotype, and the name, they have a high relationship in the ESF. We perform another EDA, which is of the scatter plot of the tick infestation. The tick, it uses the longitude and the latitude plots, which are geographical distributions, and then the color coded based ESF presence. One color represents that ESF is 0, and another color represents that ESF is 1. So let's take a quick look at this visualization. It helps to detect the geographical patterns in the disease spread. So it is right here, the geographical distribution. The pink represents that there is high chances of ESF, while the blue indicates that there are no chances of ESF. These are latitudes and longitudes, so where they meet is the place where this prediction is made. Yeah, so that's all we had about the EDA. Performed the EDA about the class distributions, where we saw that the classes are equal. We performed an EDA on the correlation of the heat map, where we saw the relationships between different features. Performed the EDA about the histograms, box plots, the scatter plot, and also the geographical distribution of EDA in different areas. Thank you.